Look at this. This is the Citadel Campus, a data center in the middle of nowhere, Nevada. And right now, inside this campus, they can run 250,000 NVIDIA chips at full capacity. This means that they could potentially draw almost 650 megawatts of electricity. That's enough to power the homes in cities like San Diego or Dallas. It's about 500,000 homes. But there's no city here, just sand, silence, and the hum of machines training AI models that don't even exist yet. For the last few years, the tech world has been obsessed with one question. When will we get AGI, artificial general intelligence? When will machines become as smart as humans, or worse, smarter? But there's a problem no one's really talking about. A problem that has nothing to do with algorithms or data or even ethics. And it might be the one thing that stops us from ever building superintelligence. It's electricity. Let's start with the idea that got us here. In 2020, researchers at OpenAI and Johns Hopkins University published a paper that changed everything. It was called Scaling Laws for Natural Language Models. The premise was simple. The bigger the model, the smarter the AI. For example, GPT-2 could, let's say, write sentences. GPT-3 could write essays. GPT-4 could pass the bar exam. The pattern seemed clear. Just keep scaling up. More parameters, more data, more compute, and more intelligence would follow. Microsoft bet $10 billion on it. Google restructured entire divisions around it. Meta hired entire departments to chase it. But there was something hidden in the paper that most people didn't talk about. For every 10x improvement in AI performance, you would need roughly 100 times more compute. But you can't just get 100 times more compute without 100 times more power, unless we build more efficient chips. GPT-2 was estimated to cost about $50,000 to train. GPT-3, nearly $5 million. GPT-4 training costs have never been publicly disclosed, but some estimates put it at somewhere north of $100 million. So what are we using to do all of this compute? And how much power do we actually need? Look at this. This is an NVIDIA H100 chip. It's the engine of the modern AI machine. Each one costs roughly $30,000, and each one, when running at full capacity, draws about 700 watts of power. That's like having 70 light bulbs running 24/7. That's almost 2 household worths of light bulbs running all day, every day. But it doesn't just take one chip. You need thousands of these chips, all running at the same time. Let's do some simple math. An AI frontier model training cluster might use 10,000 of these chips. That's 7 megawatts. It's enough to power a small town of about 3,500 homes. And that's just for training. Running the models afterwards, inference, uses even more energy at scale. Right now, data centers consume about 4% of the total US electricity. By 2030, that number could more than double to around 10%. So here's the uncomfortable question no one's asking out loud. If it takes this much power just to run what we have, how much more power would we need to run a single AGI? What if AGI isn't a software problem? What if it's an energy problem? Let's take a look at the Google data center in Iowa. It's one of hundreds around the world, and it's running into a problem that threatens the entire AI industry. It's called the power wall. Modern AI chips generate an insane amount of heat. An H100 rack can produce 50 to over 100 kilowatts of thermal energy per square meter. That's hotter than a commercial oven. In the early days of computing, you could cool chips with fans. Then you needed air conditioning units. Then you needed precision cooling systems. Now we're installing liquid cooling directly onto the chips. And even that still is a challenge. Google, Meta, Microsoft, they're all spending billions retrofitting data centers that were built just 5 years ago because the cooling systems they installed back then can't handle today's AI chips. As the need for better compute grows, we also need to design better chips. Better chips right now are hotter chips, meaning more cooling is needed. More cooling means more electricity is consumed. More electricity means higher cost. Higher cost means pressure to make chips more efficient. More efficient chips get used to build bigger models. Bigger models generate more heat. It's called the Jevons paradox. Every efficiency gain gets reinvested into larger scale. So total consumption goes up, not down. And we've seen this before. When steam engines got more efficient during the Industrial Revolution, coal consumption didn't drop, it exploded because suddenly everyone wanted a steam engine. The same thing is happening with AI. As chips get better, companies just build bigger clusters. The hunger for compute is insatiable. GPT-3's training run in 2020 consumed about 1,300 megawatts of electricity. That's enough to power an average American home for 120 years. GPT-4 used exponentially more. OpenAI won't say how much, but independent estimates from researchers put it at over 50,000 megawatt hours. That's the annual consumption of a town of about 5,000 people. And GPT-5 could be drawing 500 megawatts or more. That's not a data center, that's a dedicated power plant. Imagine how much more power AGI would take. Now, there are people trying to solve this problem. We're building chips smaller and smaller to fit more compute per square inch. The latest chips are built on a 3nm process, but going much smaller and quantum effects start taking over. Basically, we're starting to hit the limits that could impact the chips. We can't rely on shrinking transistors to make chips more efficient anymore. So scaling intelligence mostly comes from using more chips, which, unless efficiency or algorithms improve, means higher total power. But the grid wasn't designed for this. It was designed for predictable loads. Homes, factories, offices. AI data centers are different. They're like turning on a small city's worth of demand overnight, and they never turn off. In Virginia, where Amazon and Microsoft operate massive data center clusters, the regional grid operators are warning capacity shortage could happen by 2027. In Texas, AI companies are negotiating directly with power plants to secure dedicated supply. Data centers in some regions already account for a significant portion of local electric grids strain. This is strain that was never designed for this kind of concentrated demand. And here's the nightmare scenario. I want you to imagine it's summer. A heat wave just hits the West Coast. Air conditioners are maxed out. The grid is already straining. And somewhere, Meta's new AI training cluster, scheduled to launch that month, comes online. Instant blackouts. This isn't science fiction. Grid operators are already gaming out these scenarios. In March 2024, Sam Altman did something unusual. He went onto a podcast and said the quiet part out loud. He said, "We need a lot more energy than people think." Dario, CEO of Anthropic, echoed the same concern. Suddenly, everyone was saying it. The AI race had become an energy race. The UAE is already building AI clusters in the desert, powered by the sun and nuclear power. China has announced plans to build 150 new nuclear reactors by 2035. Whoever solves the energy equation first could win the AI race. It's that simple. This is why Microsoft just signed a deal to reopen the 3 Mile Island nuclear plant. It's why Google is investing in fusion energy startups that promise near limitless clean power if the physics work out. It's why Sam Altman personally invested $375 million in a company called Helion, which claims it will deliver fusion power by 2028. Fusion, the energy source that's been 20 years away for the last 60 years. But here's the thing, these companies aren't investing in fusion because they believe in clean energy. They're investing because they have no other choice. The grid just can't scale fast enough. Renewables, fusion is the only theoretical source that could deliver the terawatts of continuous carbon-free power that AGI might require. And the big question is, will it arrive in time? So here we are, the most important technological race in human history, and it's being throttled by kilowatts and thermodynamics. There are 3 ways the story could end. The first scenario is fusion works, or we build a new clean energy source to power the data centers. This represents a massive opportunity within the energy space. If we do this by 2030, energy is no longer the bottleneck. OpenAI and other companies train a new model on a cluster drawing gigawatts of power. The model could be terrifyingly good. It starts solving some of our toughest problems. AGI arrives, and with it, all of the promises. Or all of the risks. Scenario 2, the grid just can't keep up. Fusion doesn't deliver, New nuclear plants aren't supported. By 2028, the cost of training the frontier models becomes prohibitive, and we start seeing diminishing returns. The latest model is only marginally better than the previous. AI doesn't disappear, it just stops getting drastically smarter. We essentially hit a plateau. The technology becomes like search, mature, incremental, useful, but no longer transformative. We never get AGI. Intelligence remains narrow. The machines stay tools. And maybe that's fine. Maybe that's the best thing. Scenario 3. This is the dark horse. The breakthrough no one saw coming. A team at IBM or MIT or startup no one's ever heard of cracks the code on neomorphic computing. These are chips that use transistors arranged to behave more like networks of biological neuron and synapses rather than like traditional processors. Suddenly, you can train models thousands of times larger using 1/100th of the energy. This would shift the entire paradigm. Or maybe it's quantum AI, leveraging superposition to explore solution spaces no classical computer ever could. Or maybe it's optical computing that uses light instead of electrical currents for many operations. Photons can travel with far less resistance and generate much less heat than electrons in wires. So carefully designed photonic chips can run at very high speeds while cutting energy per operation. Any of these could change the equation. All of them with an energy solution would change the entire game. The real question is, will they happen in time? The AI race has always been framed as a battle of algorithms. Whose model is smarter? Whose training data is bigger? Whose researchers are more brilliant? But what if the real race is simpler than that? What if it's just who can generate the most electricity? 140 years ago, Thomas Edison built the first electrical grid in Lower Manhattan. It powered 400 light bulbs. Today, we've electrified the world. And now we're trying to use that electricity to build something smarter than ourselves. But every watt we generate has a cost. So here's the question we've been building. Even if we can build and power AGI, should we? If you want to see what else is being reshaped in tech, business, and the economy, then you're going to want to subscribe and watch this next episode right here.